start. Okay, it's a great pleasure to introduce Professor Sergio Colafrancesco, who comes now from Johannesburg. He is chair of the SKA in the University Wits in Johannesburg. And he, he's Italian and has developed his career mainly in Italy, working for the National Institute for Astrophysics. Actually, he's permanent staff also at the observatory in Rome. And Sergio has a very long trajectory on cosmology and also plasma physics at large scales, particularly working on the interactions of plasmas with radiation, like cosmic microwave background, but at many other levels. He has, as I say, a long trajectory. You did your PhD in the University of Padua, right? And after that, he had several visiting professorships in Rome, in Poznan, in many other institutes. He's a scientist involved in many important experiments. He has participation in Olimpo, Fermi, Planck, New Star, Radiostron, Core, this the mission for cosmic microwave background polarization measurements, and finally in CTA, the Cherenkov telescope array. He has more than 130 refereed publications and hundreds of talks and seminars. As you will see, he's an excellent speaker. So we are discussing here these days the participation of South Africa. He's, as I said, working at the university in Johannesburg, the participation of South Africa in the Quixote experiment and how we could jointly extend the observations to the southern hemisphere and then have full sky coverage for our experiments. So I hope that in the future we will have him as a frequent collaborator here. Now he's going to tell us about probing the nature of dark matter with the SKA. Sergio, thanks, welcome.
It's a pleasure to be here visiting this wonderful institute, very vibrant, very active, very pleasant, very welcoming, I must say. Today, I would like to discuss an issue related to the origin and the physical nature of dark matter, but in a way which is complementary to the standard approach to the search for dark matter, which, as you know, especially here in Canary Islands, is as a bias, as a physical bias, a physical strong motivation to be done mainly in the gamma rays. Let me start the talk. Anytime you want to interrupt me or ask a question or give a comment, please feel free to do it. It's more a kind of friendly discussion rather than a formal presentation. Dark matter exists, as you know. And we know we have this evidence since more than 80 years, since Fritz Zwicky in the early 30s of the last centuries discovered that in order to reproduce the dispersion, the velocity dispersion measurement for one specific object, which is the Coma cluster, you need more than the mass associated to galaxies. At the time, the mass to light ratio was extremely high, but it was for one reason, because the Hubble constant at that time was 500. And if you just use the standard value of the Hubble constant, you get that the mass to light ratio should be of the order of 100, which makes the problem less compelling, but still is a problem. Or not? Well, there are counter or complementary opinions. Dark matter is a problem for cosmology only if you assume complete general relativity, Einstein equation, no extra term in the matrix, meaning that the gravity laws is the one that we know in our universe without any correction, any modification. If you take the liberty to introduce a modification in the gravity, like has been proposed by John Moffat at Perimeter Institute, then you don't have a problem for dark matter. You can modify the gravities in such a way that you can recover velocity rotational galaxies. You can recover the mass to light ratio and the velocity dispersion measurement of cluster of galaxies. Somebody, John Moffat especially, thinks that you can even recover the lensing properties of galaxy clusters. And you can even provide a reason for the merging structure of this famous cluster, which is the Bartlett cluster. Now, in the remaining part of this talk, which is most of this talk, I will assume that dark matter is really a problem. So I assume general relativity to hold at any scale in the universe. But please bear in mind that this might be a serious way out. But let me discuss about the physical approach to discover dark matter. And in order to do that, this is basically the outline of the talk. I will discuss an historical timeline for the search of dark matter, which I believe can offer you a very important take on how we get to have this huge problem in cosmology and in structure formation in the universe. I will show you what are the techniques for dark matter search in astronomy, in astrophysics, what the optical dark matter probes are, from gamma rays and then to radio. I will discuss specifically what we can do with radio and the complementary probes, possibly, and a future outline that we have in the expectation for next years. Let me start with the dark matter timeline. As I showed you before, the problem of dark matter came in the 30s when Fritz Zwicky was a physicist. The nice things about Fritz Zwicky is that he covered a lot of astrophysical problems, being and approaching the problem like a physicist. He was working on supernova, and he proposed supernova explosion paradigm. He was working on dark matter, he was working on gravitational lensing, he was working on many, many other things. Fritz Zwicky just measured these things and found this value here that, again, you should bear in mind, has been taken with the Hubble constant of 500. That was at the time the value, you know. At the moment, if you use 70 or 100 or whatever you want, this M over L ratio gets down, but still is there. Zwicky used to write in German at the time and used the words Dunkelkante Materie, which you can translate literally in dark cold matter, not certainly in the modern way that we deal with these things, but again, this person has a kind of vision about the problem. In 39, well, in 36 and 39, a few years later, two more astronomers, Smith and Babcock, pick up the message and try to make observation of other sources, especially Smith and the Virgo clusters, that was exhibiting a similar behavior. And Babcock noticed that also that the outer region of M31 were rotating with a very high velocity, indicating a missing mass there. This was basically is the problem. I'm sure I don't need to go through these things, but basically the flattened rotation curves in the outer parts indicate that you need more mass in the halo of the galaxy. Actually, there was already a problem of missing mass, but in the local environment, in the solar environment. That was studied by Opik, Oort, Kuzmin, and a number of people up to the modern recent times, but deals with what is missing or what is not known around the local solar system, basically, which has not to be confused with the global dark matter problem, which is a real anomaly in cosmology. The problem stayed there silent for something like 30 years. Nobody really wanted to deal with this problem because it was a serious challenge for astronomers. Until in the 59, Kahn and Volcher published a discovery of what they call missing mass in the local group, but this referred to hot gas. So they realized that the baryonic content of the local group was not fully recovered by just stellar component or dust component. They need an extra baryonic gas, and this from X-ray measurement today we know that is due to diffuse hot baryonic plasma. In the 61, there was a real renaissance of dark matter, truly began with this meeting here, and by that time enough research was done for the community to see that the missing mass was not a problem that was easily put in a corner. And especially due to the work by Vera Rubin at the Ford spectrograph here, this is an image of Vera Rubin, very young Vera Rubin at that time, we start looking at the rotation curves of galaxies very far away from the center and then quantifying what the problem was. In the 70s up to the 80s, a number of cosmologists, primordial cosmologists, in the sense that they were at the beginning of cosmology, they started to produce simulations and large-scale structure formation scenarios and so on, just to include dark matter in the problem. Here you can see Jim Peebles waving hands and trying to explain Scott Tremaine what the dark matter problem was. In the 80s, one important thing is that the first experimental probe for the existence of neutrinos, so different flavors, was beginning to get evident, and there was a very famous meeting at Tallinn 77 where all people from the two blocks, East Bloc and West Bloc, they got together and tried to discuss sincerely what the problem was, and Jakub Zeldovich was the one pushing for the elementary particle nature of dark matter. This is Malcolm Longueur at the time. In the 80s, the cold dark matter problem was really getting and being considered very seriously, such that large n-body simulation took this dark matter problem into account and produced impressive images of what the sub-halo structure around the typical cluster or a galaxies was. And this created a lot of other problems. For example, the huge amount of substructure that we don't see in reality in cosmic structure, but is being or was being produced in large-scale n-body simulation. The 90s was the realm of gravitational lensing, and there was a major advancement in the discovery of dark matter because the arch shape of the gravitational lensing images tell us what the gravitational potential around cosmic structure was. There was a clear idea that there was a large-scale potential dominated by dark matter and not by baryons or gas. Interestingly enough, the idea is usually attributed by Einstein, but a century before, Johann Soldner was a geologist, introduced for the first time the concept of deflection of light rays by a massive body, without knowing anything about general relativity, of course. There were, along this timeline, a number of false alarms at diversionary maneuvers. The false alarm, one of the most clear and well-known false alarm was due by Johann Hort, who was trying to put the idea that the presence of missing mass in the disk of the galaxies. But this would have created a number of dynamical problems which turned out to be impossible. So it was a kind of proposal, not turning out to be very realistic, but it was an attempt. And the other one by Mordecai Milgrom, it was the introduction of modified gravity, the MOND scenario, in which you substitute the potential due to an additional matter component with a modification of the metric due to a modification of the low gravity. And this is still well known under more general ways like Teves or modified gravity and so on and so forth. The end point of the discovery of dark matter in the last century came with the discovery of small-scale fluctuation in the cosmic background radiation. These are probes of dark matter. The amplitude and the spectral distribution of cosmic microwave background fluctuation depends on the dark matter amount. This bar here shows you how the spectrum changes with changing of the dark matter component. So if you want to measure the spectrum of anisotropes at the level which is given by the observation, you immediately require a global amount of dark matter. And that closed the circle at the end of the century. By that time, the idea of the nascence of a true astroparticle physics community around the dark matter problem, putting together people coming from astronomy, measuring rotation curves, for example, of galaxies, and people coming from the particle physics world, proposing scenarios of fundamental interaction producing a mass of the dark matter particle or interaction, was really coming together. So all in all, I can say honestly that most of the evidence and most of the progress in dark matter has come through the astronomical community. And what the particle physics community provided is just hints on the possible existence of an elementary particle or a complex bound of elementary particles producing a candidate or many candidates for dark matter. The circle is now closing here, but not yet fully closed, because we don't know yet what is the fundamental particle of dark matter. We are trying to discover it. In the last few years, there was a huge amount of interest from the community. And we actually have evidence for discovery of dark matter many times. From 2009, has been announced that CDMS data at 10 GeV WIMP was discovered, up to the recent 2014 evidence for a macro electron volt axion paper. Only in the last year, we had 4 more evidence for discovery of dark matter. No one truly realistic, of course, but there were, announcement, very strong announcement about these things, of evidence of self-interactive dark matter, Fermi-like dark matter found in the reticulum dwarf galaxies, dark matter found in the Milky Way core, which must be there because otherwise the Milky Way cannot sustain itself, or sterile neutrino found in XMM XA satellite. But this was coming not only from the astronomical community, also from the particle physics community. There was a major announcement from the CEO of CERN late last year saying that AMS2 measured the positron fraction, and this was a clear indication of the presence of dark matter in the solar, in the local environment. Now, of course, we know that dark matter is not yet discovered, it's not yet being detected, and we have only hints on the presence of dark matter, and this is why we are continuing our search. At the present, the dark matter evidence comes only from its weight. We can wait with gravitational lensing, we can wait with rotation curves, we can wait with other techniques, virial theorem or whatever. We don't know anything about the physical nature of this particle. Now, this comes to the second part of my talk, how we can get ideas of the physical nature of this particle. Well, first of all, we have to start from the fact that dark matter exists under the assumption that general relativity is dominating the universe. The dark matter is mostly non-baryonic, otherwise we should have discovered already in many other ways. And the dark matter is very elusive. So we must consider unambiguous evidence for the detection of dark matter. And we need crucial probes for that, not just generic probes. Now, there are 2 kinds of probes, which I call inference and physical. Inference probes comes from virial theorem, hydrostatic equilibrium, gravitational lensing. So you just have a gauge and you measure how much mass is in the system. Physical probes comes from signal associated to the either annihilating or decaying particle of dark matter. In the case of annihilation, you produce from supersymmetric particle, let's say, for example, standard particle. Once you produce standard particle, you are in the realm of astronomy. You can do an experiment, you can make an observation, you can measure a spectrum or a continuum spectrum, a line or whatever, you get a signal. If the signal is unambiguously associated to this phenomenon here, you discover dark matter. And the same is for the decay. You just measure a line or a combination of lines. Now, these interference probes, since they are subject or vulnerable against Mond, Teves, so general relativistic variation of the Mond theory, are vulnerable against modification of the metric. So you are never sure, just weighting a system, whether you measure dark matter or you probe modification of general relativity. What is crucial is to test these emission properties through electromagnetic signal. And this means that out of dark matter interaction, annihilation, or decay, you just illuminate a dark matter halo. You produce standard radiation, which is what we want to do in astronomical context. And of course, you want to have clean and clear properties of the system that you want to measure dark matter. Now, for example, you should avoid a system with a lot of star formation, a lot of atomic or diffuse gas, possibly jets and other complicated non-thermal mechanisms. What you want to have in an ideal world is a pure dark matter halo, only dark matter or mostly dark matter with a little bit of other things like stars, because otherwise you don't know whether it is a gravitational system or not, a little bit of gas and so on. But you want the mass and the physical content to be dominated by dark matter. Otherwise you are always in trouble. You get back to this case here. I consider 3 viable dark matter candidates at the moment. There are many more. I think physicists have been extremely clever to produce something like 30 or maybe more reasonable physical candidates, each one very reasonable, okay? But let me take the one that are at the moment more widely discussed. The first is Neutralino, typical supersymmetric pattern, which is not excluded by LHC measurement. I want to make sure. The announcement that has been done last year was not excluding a typical supersymmetric Neutralino pattern. The other one, and the typical interaction are that you produce charged pions or neutral pions. You go from decay of this particle into electromagnetic signal, and the signal is, the flux is basically depending on the square of the neutralino mass, the inverse square of the neutralino mass, the cross-section which gives the normalization of the signal, and a number of electromagnetic features that produce the spectrum. The other one is axion-like particle dark matter, in which you have a photon magnetic field interaction. You convert the photon into a magnetic field. You absorb or you emit the photons. You get modifications along the line of sight from the source to your telescope. And you get modification of the spectrum. You can measure in principle the axion mass, but this is very highly degenerate because you don't know the coupling constant, you don't know the magnetic field amplitude and the domain size of the magnetic field. The third one is stellar neutrinos, in which you have basically a radiated decay line at the energy where the stellar neutrino decays in normal neutrinos private flux. Now, since this mass here is much less than this mass here, basically you measure a line at the same energy on the stellar neutrino. I will discuss mostly this part here because this gives you the possibility to my colleagues in the SKA to measure synchrotron radiation, while it is almost impossible to do it in the other ways. And this is basically what we get. We get the synchrotron branch emission from secondary leptons spiraling onto a magnetic field. We get branch traveling in this Compton pi naught decay and a line at the annihilation energy. Here you get spectral modulation in the case of ALP, and you get a line here. So very different spectral predictions. Now, in the case of supersymmetric dark matter, you get 2 dark matter particles. They annihilate, they produce pi 0. They decay immediately into gamma rays. They get a pion bump. And you get charged pions. They immediately decay into electrons and positrons. And once you have electrons and positrons and the radiation field or the magnetic field, the work is done. You can produce a lot of radiation mechanisms, from inverse Compton to Bremsstrahlung to radio emission by synchrotron and so on and so forth. So this is a very economic way to produce normal radiation. Use your telescope, either gamma, X-rays, radio, millimeter, whatever, and then measure the signal. And if you're lucky, you get the typical, very clear spectral signature that you can associate then to the dark matter particle. There is a little bit of complication. In the case of straight gamma ray emission through decay of pi naught, you have a prompt gamma ray emission. The decay time of a pi naught 10 to the minus 17 seconds. And you get from a pion, you get just 2 photons. So you don't need to solve a diffusion equation for the energy losses and the diffusion of this particle, because the pion, every time you create a pion, this decays into the gamma. And this is why the gamma ray approach to detect dark matter is very promising, because it's a clear evidence for the presence of a pion decay. But we have to take a multi-frequency approach, which will be really the crucial probe for the existence of dark matter. So we need to consider also leptons. And for leptons, you must consider the fact that these electrons are produced once the pi naught, the charged pions are decaying in 10 to the minus 16 or minus 15 seconds, and then they can lose energy by interaction with the radiation field, the magnetic field, and they can diffuse away from the production place. It depends on the physical configuration of the environment where these electrons are produced, and they survive. I will give you an example about it. But in the case in which the loss time scale is much less the diffusion time scale, everything is confined within the halo of dark matter. So the electrons do not have time to diffuse away from the production region. In the case in which the diffusion time scale is much shorter than the energy loss time scale, you have a very serious and nasty process. You produce the electrons, it diffuses away even for kiloparsecs or megaparsecs in some case, and then only here they produce radiation. So you need to recover back a spatial correspondence between the electrons produced by dark matter and the place where the dark matter was. But you can do it. This is just to give you an idea of how important is the diffusion in a typical dark matter density profile here for different values of the size of the halo. For a 1 kiloparsec radius of dwarf galaxy, something like that, diffusion is dominating. For a typical galaxy, 10 kiloparsec or so, diffusion is important, but in the central part you can still survive with standard non-diffusive approach. In a galaxy cluster, you are not affected at all by diffusion. So everything that is produced in terms of dark matter annihilation within a cluster remains within the cluster. Now, energy losses versus diffusion. Which is more important? Well, you have to consider that every energy loss, synchrotron, inverse Compton against CMB, for example, Bremsstrahlung, Coulomb losses, and diffusion. Now, if you increase the magnetic field, synchrotron losses become dominant. So magnetic field knowledge is extremely important to understand where you are doing dark matter search. If you decrease the environment density, then the Coulomb losses goes up. So they are not very efficient, so you can neglect them. If you decrease the radius of your dark matter halo from a megaparsec to a kiloparsec, then the diffusion are extremely important, as I showed you before, and these are dominating the whole energy losses components. So you have to be extremely careful of measuring what is your spatial extent of your dark matter halo and what is the environmental properties of your environment. You can do all of these things. I don't want to bother you with all the details. What you get, what is interesting, is a branch of emission which goes from radio to very high energy gamma rays. This part here is the pion bump, which is a prompt emission. Every time you get two dark matter particles, two neutralinos annihilating, they produce this pion bump. Very clear signature. This is why we want to observe these things with Fermi, possibly with MAGIC, Hess, CTA, and so on and so forth. Very clear signature, but not easy to observe because of the sensitivity of this gamma ray experiment. So we want to go to the inverse Compton branch here and to the synchrotron branch here, which is the domain of SKA. But in this case, you are dominated by leptons. You have to take into account energy losses, diffusions, magnetic fields, and so on and so forth. You can do these things, and this is a typical case in which I force my model to reproduce the Coma radio halo things. Just to show you an example, I can do it very nicely, and then what I see here is it's strictly correlated with what I will see in the X-rays and what I will see in the gamma rays. So the very powerful method is to cross-correlate what happens in radio with what happens in X-rays, what happens in gamma rays. And then the spectral signature is so unique that you are almost sure that this is dark matter annihilation. Of course, this depends on the magnetic field, because the synchrotron part of the spectrum depends on the number of electrons produced by dark matter annihilation, but also the magnetic field that produces synchrotron. So you can change the spectrum by changing the magnetic field, and the relationship between the normalization of your dark matter signal cross-section here against magnetic field is this one. So a low level of magnetic field, in order to reproduce the data, you need a high cross-section, a large number of secondary electrons. A very high level of magnetic field, you can survive with a very low level of cross-section for annihilating dark matter. So you have less problem with the overall constraints. Your life is a little bit easier. But you have to justify magnetic fields of the order of tens of microgauss, which is not that easy. Now, let me show you what usually we do in order to use this multi-frequency constraint. I took here the most recent constraints from a number of proposals for detection of dark matter or constraints on dark matter. First, I took this square here, which is the area in cross-section against neutralino mass identified by AMS2, Fermi positron excess, and Pamela positron excess here. And I took this point here because this is the only consistent with the recent Planck exclusion plot from the overall CMB fluctuation spectrum. This was the recent WMAP 90-year constraint, so Planck has improved by almost an order of magnitude with respect to that, which proves that CMB studies is very important for these things. Then I considered the standard thermal relic, what is the amount of dark matter in terms of cross-section that is needed to reproduce the overall problem of dark matter in the whole universe, to create structures out of dark matter in the universe. Then I took what is the region contained or identified by the Fermi lat experiments in terms of galaxy, galactic center gamma ray excess measured by the Fermi lat experiment. I took 3 typical models, one maximal, one median, one minimal here, just to make an exploration. And then what I did with all these things, I took this limit here, this point here, this 3 point here, and another point related to the recent claimed excess of gamma rays towards the Reticulum 2 dwarf galaxies recently announced or recently proposed a few months ago by Fermi and Fermi-related people. And I applied these models to 3 typical structures. One cluster of galaxy, Coma, for which I have the widest range of data available, because I need data to constrain the model. A typical galaxy, M81, and a typical dwarf galaxy, Draco. So the model that I consider is a matrix model with a mass of neutralino from 10 to 500 GeV, just as an example, and composition which goes to from tau plus tau minus, BB bar, and in case of high masses, W plus W minus. So it's a matrix of models. I just plug in these neutralino models. I took this cross-section here and this mass here for these models, and I want to see whether these models are consistent with the data on Coma, M81, and Draco. That's to probe that these models are really telling us or can tell us something about dark matter. For Coma, the models cannot stand. They produce an excess of radio emission that we don't observe. They produce an excess of gamma ray emission at the Fermi lat limit for Coma for cluster of galaxies. If I use the AMS2 Fermi Pamela data plus the galactic center results, including a Navarro-Frankel-White density profile, which is a spiky profile. If I use the Reticulum 2 Fermi lat results with the Navarro-Frankel-White profile, against the situation is worse. I overshine the radio halo image of Coma by 2 orders of magnitude. So Reticulum 2 cannot be produced by annihilation of dark matter in gamma rays. It's a different astrophysical approach. But then I say, okay, but the density profile of the dark matter is too steep, produce too many annihilation. Then I use what the Fermi people try to use, the Prada, which is extremely flat, avoid an overproduction of signals. But even in that case, I overproduce at high frequency the radio emission of Coma, and I have problem with the gamma rays here. So these models here, including the Reticulum 2, cannot provide a consistent test with the emission of the Coma cluster. So the Coma cluster signal from dark matter exceed the observation. That is clearly inconsistent. The same holds for M81. As you can see here, I did the same exercise. I played the same game. And again, the reticulum 2 is the worst case in such that it cannot be produced by dark matter annihilation, as some people claimed recently. But also the AMS2 Fermi and Pamela data are heavily inconsistent with the data of MMT1. And the same holds for Draco. I just plugged the same models, I put the same things, I just changed structure. So, conclusion. AMS2 explanation, the dark matter explanation of AMS2 is not valid. The dark matter explanation of the Fermi positron excess is not valid, and the same holds for Pamela. Because otherwise you should have seen already dark matter signal everywhere. The recent claim of the Fermi lat excess in gamma rays of reticulum 2 dwarf galaxies cannot be produced by dark matter. And the galactic center excess can be marginally consistent with the limit, provided that the magnetic field is high enough that I request a low amount of electrons produced by dark matter annihilation, which means a low cross-section of annihilation. And this is what is the magnetic field request in order to be consistent with the galactic center emission. Now, what is the next step? Next step is that we have to increase our sensitivity, because the present day experiments that claim that dark matter is already detected or is at the level of detection are not enough to go deep enough to probe the real signal that we expect from dark matter annihilation. We know otherwise where dark matter is, because we know that dwarf galaxies have a high mass to light ratio. We know that galaxies' rotation curves are dominated by dark matter. And we know the cluster of galaxies have an overall mass which is justified only by a cold dark matter component, which is massively abundantly dominating. We need to improve the dark matter search, which is basically an issue of sensitivity. So we need to build experiments with the highest possible sensitivity. Dark matter search is not an issue where we can find dark matter. We already know where dark matter is. Dark matter search is only an issue of sensitivity. We need to go a generation beyond Fermi. We need to go a generation beyond possibly Hess. Possibly we need to go even a little bit far from CTA. That might be the case in some of the models. And we need to go a generation beyond X-rays and radio experiments. And this is why I want to discuss in the last part of this talk what we can do with the SKA, which is the highest sensitivity radio telescope ever conceived. Just to give you an example, this is what we can do in terms of constraints on the annihilation cross-section with the next generation X-ray telescope, which is called Astro-H, which is supposed to be launched by JAXA in Japan early next year. So Astro-H is a very sensitive telescope in the inverse Compton branch of the dark matter annihilation part. And we still begin to see something, to be sensitive enough to say something about the dark matter composition here. But the real advance will be done with the combination of CTA and SKA. Here I plot a plot of the models of dark matter, available models of dark matter, in terms of direct detection probability of cross-section and indirect detection cross-section here. So this part here has already been exploited. We know that dark matter is not here. But the amount of models that are still available is huge. And we can reach this kind of sensitivity only if we use astrophysically SKA and CTA. That's the only hope that we have, in my opinion. There is no other hope if we want to do a proper search for dark matter signal in astronomy. The other interesting thing is that astronomy will remain, dark matter search will remain an astronomy-related challenge. A recent work by, a few years ago, by Gianfranco Bertone et al. Showed that even if you take the more optimistic case for LHC discovery of a supersymmetric candidate with a future LHC and plus CTA, you still, LHC only is highly degenerate. They cannot tell us anything which is clearly focused on dark matter. The combined user LHC plus CTA will restrict the region even more, but still at the level that you get some degeneracy in the mass of the particle. And only when you use the combination of CTA, SKA, and possibly accelerators, you can get very close to the proper nature of the supersymmetric particle. So the message, the second message that I want to give is that dark matter search has been initiated by astronomers. It will probably be concluded by astronomers. Let me now come to radio emission. Why we want to use radio emission from dark matter to probe it? Well, radio emission is another way of probing the same physics that you can probe in gamma rays. Only the physics is a little bit more complicated, as I showed you before. But it's basically telling you exactly the same. Now, let me show what we can do. I will just show you a few slides about what we expect theoretically, what are the predictions, and what are the problems. Because doing a radio measurement of dark matter is not that easy, but also what are the opportunities. The basic idea came more than 14 years ago, where in a paper that I did with a particle physicist, Barbara Mele, I just was looking for an alternative model to reproduce the radio emission of the Coma cluster. And since we have a problem, in cosmic ray physics, we produce just power law spectra, and the Coma cluster spectrum is curved. So one natural way is to use a dark matter annihilation, which predicts very naturally curved spectra. And to do this, I had to learn about neutralino physics, and this was my initial take on this very interesting piece of physics. So this is basically the same, the problem. We have a bunch of data, the Coma radio halo data, and neutralino annihilation are naturally curved, which is extremely fascinating, that you can reproduce an astronomical observation clearly and mostly uniquely with the fundamental physics process. The typical features of the dark matter synchrotron emission are that there is a diffuse emission, has a specific surface brightness, which is produced by a combination of dark matter distribution plus a diffusion of electrons. It has a wide frequency spectrum going to megahertz to tens of gigahertz. It has a very sharp low frequency cutoff, but also very sharp high frequency cutoff. And the high frequency cutoff can tell you exactly what is the mass of neutralino, as I'll show you in a minute. And there's a very low polarization level. I'm sorry for polarization experiment, but dark matter is by inherently low polarization because it's a completely spatially symmetric problem. Annihilation is occurring everywhere, and it's the kinematics of the annihilation is such that you don't expect any high polarization level. But polarization is a key way to identify possible sites. So if you find a structure, a cluster, and you find blobs that are not identified with any known source, and they show a very low level of polarization, even below the typical synchrotron level, then these are good candidates for dark matter. Now, the cutoff here tells you about the composition of the neutralino, being BB bar or even W plus diagonalized here. The composition changes also the spectral shape, which is very nice because we can learn something about the composition of the dark matter particle from the spectral curvature of the synchrotron emission. And the lower cutoff gives you a lower limit to the neutralino mass, and the upper limit gives you an upper limit on the neutralino mass. Just because you cannot expect a radio emission at frequencies larger than the energy of the electron, the maximum energy of the electron produced by dark matter annihilation. And this is related to the neutralino mass. So imagine that a neutralino has a 100 GeV mass and produces electrons from the rest energy of the electrons 200 GeV. And now the frequency is related to the mass of the neutralino, or the energy of the electrons. So you cannot expect an emission in radio at a frequency higher than the energy of the electrons corresponding to the neutralino mass. So it tells you exactly what is the upper limit of neutralino mass. And if you see the sharp cutoff at very high frequency, it tells you exactly where the neutralino mass is. Diffusions. In diffusion-dominated system, then diffusion changes the spectrum, very nasty, and changes also the amplitude, because you spread electrons from the center to the outer parts. You have to take into account these things for galaxies and galaxy clusters. And lastly, magnetic fields. You need a measurement of magnetic field which is consistently and simultaneously done with the measurement of the spectrum of radio emission, because otherwise you're stuck. There are a number of ways. One is Faraday rotation, but you need background sources or internal sources, and the medium. The other one is polarization in synchrotron, but it's difficult because we expect low level of polarization. The other one is combination of synchrotron and inverse Compton from the same object, and the ratio of the two fluxes gives you straight away an idea of the overall magnetic field. There are other two techniques which have been proposed. One is ALP gamma axion photon mixing, but this is highly degenerate with properties we don't know yet. So it's kind of needs to be avoided. And the other one, which I really, as a didactical approach, I would like every student to avoid, is equipartition. Equipartition is just a rough assumption, and it's a declaration that we don't know the physics of the system. So please, even though you can find in many papers that a standard way to determine an overall value of magnetic field is equipartition, try to avoid it. It doesn't tell you anything. At the moment, we are so hungry to get evidence for dark matter that we try to propose observation in radio. We had the idea that the sensitivity of present-day telescope was not great, but we tried anyway. And we get 120 hours of observation with the ATCA in Australia, and we pointed 6 dwarf galaxies in the local environment. These are the galaxies here. This is a typical field. You can see that there might be a diffuse emission, but your emission is dominated by point sources. And this is an interferometer. So you have to take care about the reconstruction of the primary beam and the interferometric pattern and so on and so forth. We did it, and this is the mosaic observation that we did around the typical dwarf. Just to give you an idea, these are the signals that we get. Very noisy, at the level of the RMS of the observation. Not easy to get even with this observation, which is the deepest observation on dwarf galaxies that we can get at the moment from radio. Something like 20 to 30 hours of observation per single dwarf galaxies. Not in precedent, but still at the limit. With a little bit of priors, let me say, we can get an idea of what is the level of diffuse emission in radio provided by cosmic rays. We cannot avoid the possibility that this diffuse emission could be produced just by non-thermal particles, not dark matter, or by star formation activity. We know that star formation is related to radio emission. Okay? We need to understand what is the expected level of this emission. We also need to understand what is the magnetic field that we can expect in this structure, so that we can disentangle the two things and get an idea of at least a constraints on dark matter. We did these things in, I believe, a quite honest way, and we get some results here saying that we are marginally confident that diffuse emission and star formation in dwarf galaxies is not dominant. But still, we have a degeneracy in these things, to be honest. These are the limits in 3 approaches. One is a pessimistic approach, in which we say that we don't know anything about the diffuse component by cosmic rays in the magnetic field. Even in that case, we are consistent with what are the present day limits from Fermi-Lat on dwarf galaxies. And even in some case, a little bit better. So it's a promising approach. An average way is to say that star formation is not dominant and cosmic rays can be estimated by the limits on the diffusion of electrons in the other parts of the galaxy that we don't see. And the third one is optimistic, in the sense that we say that star formation is at the level of 10% of the flux, and cosmic ray emission in radio is again at 10% of the flux. In this optimistic level, we reach values of the cross-section 10 to the minus 30 centimeter cube per cent, which is unprecedented, of course, but this is the general, to be honest. It's just showing you what is the power of this approach. With this approach, in the optimistic, average, and pessimistic, we compare with the present day limits, including limits in X-rays, in gamma rays, and so on. We are at the level of the average, which is a kind of good compromise, consistent with gamma rays limits, and so on. We think we can do a little bit better in the next few years, either in terms of annihilation, dark matter, in terms of decay dark matter here. We tried the same approach with the Ballet cluster. The Ballet cluster is clearly a cluster where dark matter is offset with respect to baryons. Here, this is dark matter reconstructed by gravitational lensing, and this is baryons here. And interesting, we see that the radio halo emission is elongated towards the region dominated by dark matter, which is very interesting. So we get excited about that. And here you can see how the radio halos does not correlate with the X-ray emission, but correlates more with the position of the dark matter peaks. And in particular, this source here is a point-like source, which is not identified with anything, not even a star or a galaxy and so on, and is our best bet for a possible sub-clump of dark matter in this radio emission. I'll show you why we think like this. We did an analysis. We indeed realized that the overall spectrum of the radio halo needs at least two components. One done by standard cosmic rays, accelerated electrons and so on and so forth, and the other one flatter, which might be recovered by a typical standard dark matter annihilation model, which are quite flat, especially when the mass is rather high, like 500 GeV or so. We tried to keep consistency between these findings here and what we expect in sonizatory effect, in gamma rays, and so on. So this expectation here, with very extreme values of the annihilation cross-section and magnetic field, are consistent with the Fermi CTA, well, Fermi limit for sure, and the prediction of Astro H and CTA. So we are sure that with this explanation here, in terms of an additional component by dark matter, we are not violating any existing limit or any future limit that we want to have. But again, we need an annihilation cross-section which is rather high. This can be done by assuming that there are substructure on top of the overall dark matter density profile, which enhance what we call the boosting factor. Annihilation of dark matter is a two-body process, so it's proportional to the density square. If on top of an average density square you put clumps, you amplify non-linearly the normalization of your dark matter signal. So this value here can be recovered with a standard relic density cross-section plus a boosting factor of the order of 1000, which in Navarro-Franke-White density profile is not that extreme. In some cases in which we can maximize the magnetic field not at 10 microgauss but a level of 20 to 30 microgausses, then we can decrease the boosting factor by, let's say, factor 5 to 10 or something like that. So we might be pretty consistent. It's something that we have still to double check and verify, because this is the first time that an analysis like that has been done. But this tells us that there is another way to probe dark matter. And this is a simulation of a typical cluster. So the technique that we are exploring at the moment is just not to go for the full dark matter signal in terms of radio, This is an idea of simulated map at 1.4 gigahertz of a typical cluster, observed by SKA. But we want to perform a dark matter analysis in video, just pointing out subhalos. Subhalos which are not identified and not cross-correlated with any known source. So basically we are highlighting subhalos with the highest value M mass to light ratio, which maximize the dark matter presence, and the highest values, the lowest values of stellar fraction, which minimize the radio emission from star formation rate. So we are going to very low mass halos here, which are consistent with these two requirements. Look for simulation for real observation, for example, pinpoint regions where you don't find star formation, where you find subclumps, no identification in multi-frequency catalog, and make a deep radio observation as to probe if there is a chance to detect some spectral feature which is consistent with dark matter. There are problems, of course. First of all, you need a very huge frequency range. You need a large field of view. You need an extremely high sensitivity, order of microjansky or better, which is not achieved at the moment. You need a consistent simultaneous measurement of magnetic field. Without this, out of game. No way, no chance. And you need a very clean and very effective process of removal of contamination, source and diffuse. This is what the SKA can do. I don't want to keep you tied up with what the SKA is. I'm sure you know very well what the SKA is. Just to give you a few numbers here. It has a huge frequency range. It has a huge sensitivity, an enormous survey speed. You can detect the level of microjansky in 10 hours. A typical dwarf galaxies down to, as I said, nanojansky level, 100 nanojansky, which is what you need. We are now here, more or less. The site selection has been done. We are waiting for the delivery SKA phase 1. We will be waiting for the delivery SKA phase 2, and in 2024, possibly, we will have the full SKA. As you know, the SKA site is split in two. We have the very low frequency array down in Australia and the mid-frequency array in South Africa, with a VLBI structure extending from South Africa up to Ghana at the moment, possibly up to here, one out in Canary Island. It will be the largest baseline for mid-frequency radio telescope in the world. What is really good for dark matter search is that the sensitivity SKA phase 1 and 2 reaches something sub-microjansky level. This is what you need. As I show you a few slides before, dark matter search is just a matter of sensitivity. There is nothing else. And, more important than all, with the SKA we can measure fluxes and spectra, and at the same time we can measure magnetic field through Faraday rotation. This is an idea of how many Faraday rotation per field of view we can get with the SKA simultaneously. We can get up to 300 RMS per cluster in 13 clusters in this frequency, in this redshift range, or 10 RMS per cluster in 2000 clusters in this high redshift range. This is the kind of simulation that you can get, but not only in cluster, also in galaxies. This is a typical data available at the moment for M31. This is what SKA is expected to do. So the study of galaxies would be revolutionized in terms of SKA at this level. And of course, it will provide us the best possibility to study dark matter in galaxies and clusters and all other structures. From the work that I presented before and the 6th dwarf galaxy here, with the SKA we expect to be here in only 30 hours of observation on a single target, the same galaxy, dwarf galaxy. So something like 6 order of magnitude better with flux, spectrum, and magnetic field measured at the same time. Of course, with this sensitivity here, we can put an horizon. What is the maximum redshift for typical dark matter halos that we can reach in the universe with this kind of study. So enhance the statistics and make the study of dark matter really an overall study. This is with the typical relic cross-section here, and we have a number of targets that we can study very clearly in our universe, clusters, galaxies, and a bunch of dwarf galaxies. But even at this level, at 10 to the minus 30, in terms of annihilation cross-section, this is the horizon here. We still have a few objects to be measured with the SKA. In terms of bound that we can put on cross-section according to the various typical dark matter particle channels and masses, these are the constraints that we can put with a typical cluster, a galaxy, and a dwarf galaxy. Of course, clusters are the best candidate because they contain the largest amount of dark matter. We can have a lot of annihilations and a lot of flux. What we can do at the moment? Well, at the moment, what we are trying to do is just to push for any possible radio observation that we can get at the moment in order not to realistically detect a radio signal, but to maximize and ameliorate or refine the strategy for search, and especially the strategy for removal of point-like sources and diffuse components, and the strategy for getting a reliable amount of reliable values of magnetic field. But by 2020, we will be in the unique position to have 3 major experiments in the world that will tell us whether dark matter is really made of particles like neutralinos or not. And these are SKA, working in this range here, CTA, working in this range here, improving the pion bump decay, and a large millimeter space observatory that hopefully will be available by the time a few years later, which is called Millimetron here, that will prove either the high frequency radio cutoff, telling us straight away what is the neutrino mass, or the inverse Compton part of the emission here, telling us what is the overall magnetic field that we have to expect in dark matter halos. And thank you very much for your attention.
Thanks a lot for this excellent review. We have little time for questions. Yes.
Doctor, you have been using the neutralino as the main component of the dark matter.
Yeah.
Well, you have described the model and so on.
Yes,
So
yes.
I was wondering whether from the fundamental physics or the most advanced theoretical ideas, do we have any hint of what could be the most favorable? Because you have discussed many, but I mean, we can say neutralinos would be 30% of dark matter, axion 45 or so. So do we have any kind of idea of this?
I think that from astronomical point of view, let me put it this way, we should approach the problem in a conservative way. We should first, this is my approach at least, we should be very conservative, saying that we want to approach the single component dark matter, neutralino 100%, and see what we can get. If we are consistent with something, then that's it, or at least it's dominant. If we are not consistent, then we have to go for a more complex composition, not just in terms of neutralino physics, but also in terms of other things. But the relation between radio, microwave, and gamma rays will tell us also whether in the same structure we can see, for example, spectral variation or wiggling of TV sources for CTA, for example, that will tell us what is the amount of ALP things there. The XA, the next coming XA or UV missions will have the spectral resolution to tell us something about these neutrinos. But I'm not fully convinced that we know the fundamental physics of the plasma, which are in cosmic structure, just to disentangle the possible line emission due to the sterile neutrino decay from fundamental plasma physics. That's a completely new...
I agree with you, but the point is that in the baryon side, let's say we have many particles, many different particles. So why should we expect that in the dark side, let's say?
No.
I mean, in fact, I would expect that there would be many different kind of particles.
You are completely right.
Okay, and I was wondering whether theoretically people have suggested or I mean, we are completely blind on that, I understand.
Totally blind. But this is why astronomical research is very complementary, because if you still rely on only particle physics, you remain in this blindness situation. In astronomy, you can see spectral feature in many frequencies, and this will help us to tell, look, in that case, we are kind of confident that we are looking this kind of particle physics in dark matter. While in the other context, we can see that, no, maybe it's a composition of two things. And then it will be a matter of just building up a very consistent, self-consistent astroparticle physics scenario that will bring together constraints from astronomy, put in the laboratory of accelerator or whatever, and then modify the particle physics experiments such that they will be addressed to the specific problem.
Okay, last one.
Could you, well, you have been explaining predictions of the emission of dark matter from galaxy clusters to dwarf galaxies, but why is it easy to understand why you do not expect a signal from clumps of dark matter in our neighborhood?
Yes. I took just 3 typical examples, and I took this example because I have data on the structure. I don't have data on clumps of dark matter traveling in the galaxy, at least so far. So what I want to use is clumps of structure, cosmic structure, which have the largest amount of observational data. And these are dwarf galaxies and clusters on 3 typical dark matter scales in order to challenge the prediction of dark matter against this data. Of course, you are perfectly right. There are subclumps or subhalos that are traveling at even high velocity around the solar system. If you consider that we might have 10 to the minus 6 solar masses, even 10 to the minus 9 solar masses, as now the large-scale simulation are predicting, floating around the galaxies, that you can have a lot of dark matter signals coming from these halos. But it will be a very degenerate prediction in the sense that it will be very difficult to say that this emission is due only to dark matter rather than a composition of unknown physics in this structure. The advantage of having cosmic structures which are well known is that there are a lot of data. And dark matter has the beautiful prediction that it covers spectrally signals from the very low frequency radio, megahertz frequencies, up to extremely high frequency gamma rays energies. And in order to be consistent with dark matter explanation, you have to be consistent with all the prediction. And then you need data to challenge with.
Thank you.
Okay, we can move the discussion to the science coffee, and please let's thank the speaker again.
Thank you very much for your time.